Thank you. Right, good morning all. Everybody good? I'm not sure how to follow that, by the way. I'll try. So I'm going to take you on a journey this morning. And it's a journey through diagrams and maps and software architecture. Let's imagine the year is 2026 and teleportation has finally been created. And I teleport you here. How lost do you feel now? Where are you? A leafy lane somewhere? La Rue looks French. How do you solve this? How do you solve this problem? How do you get out of this mess? Well, you could walk along the road and ask people where you are. Zoom out, yeah. So you get your smartphone out, you open the Maps app, you press the dot button, and it shows you where you are, and you zoom out. And you get something like this. So now where are you? You have to zoom out again, yeah. Oh, so now you're in Jersey. This is where I live. So this is a small island off the coast of France, 9 miles by 5. There'll be a little dot here somewhere. This map's kind of complicated, isn't it? It's very cluttered. There's lots of textures going on. It's hard to see what the place names are. How do we solve this problem? How do we make this map clearer? We remove the satellite imagery. Aha, now it gets clearer. So this is Jersey. Now you can see the intricate little network of lanes and roads and things. Do you know where Jersey is? Nope, we zoom out a bit further. There we go, there's Jersey. This is where I live. Zoom out some more. Zoom out some more. There we go. So there's Jersey. It's a small island just off the coast of France, tucked away down here. Who's been to Jersey here? That's terrible. So next summer, on your summer vacation, when you come to Jersey, when you walk through Jersey Airport, you should pick up one of these things. It's a visitor guide. And the visitor guide tells you what you need to know about Jersey. And more specifically, it gives you a set of maps to help you start exploring. And the maps look like this. It's a very simplified view of Jersey. Doesn't tell you everything. It tells you just enough to get around and to start exploring. This is where I go surfing. For Edwards, wherever he's gone. This is where you should come surfing as well, Edwards. There is a little zoom in on the town area. Again, it's got some street names and some place names, a bit more detail here. This is not entirely accurate, I must say. So this blue bit here looks like water. It is water half of the day. So don't park your boat here and expect it to be floating, because I guarantee it will not be floating all the time. And this thing over here is a bathing pool. It's like a little seawater swimming pool. And it looks like it's isolated by beach. It actually does get flushed with seawater twice a day, which is handy because in the summer the kids pee in there. So it's not entirely accurate, but it's a good start. If you contrast this with an Ordnance Survey map, this is a very precise, detailed model of a landscape, an environment. And you can see every single street and road and house and building on here. And this takes a lot of effort to put together. Now, in the software world, we can do neither of these things. Really, what I want to do is create a set of diagrams that act as maps on top of the source code. And we are absolutely useless as an industry at doing this. So one of the things I do, one of the things I'm doing tomorrow, is I run a software architecture diagramming workshop. And during that workshop, we break people into groups of 3 or 4 people. We say, here are some requirements. Go and design a solution for this set of requirements, and draw some pictures to describe it. These are the pictures we get. So I promise I have not made any of these pictures up. This is just a shopping list of technologies, not particularly useful. This one is boxes and no lines, because it has boxes but no lines. Doesn't really tell you anything about the structure of the solution. This one is what people normally refer to as a functional view. Imagine you've bought some land, you're having a house built, you ask your building architect to draw you a functional view of your house. Eating, sleeping, dining, entertaining. Right, it's not particularly useful. Stormtroopers, little face clones attacking your system. This is bad. Please name people. I love this one. This is like those airline route maps. So that's Schiphol or Heathrow. It's like a big airport hub with lots of routes around the world. That thing's important. because everything is pointing to it for some reason. And over here, look, it's just a car crash of different lines and boxes and colors, and that box there says UI. Do you know why it says UI upside down? Because people were sitting on the other side of the table. That's it. It's just pure laziness. This architecture diagram represents every single system you are currently working on. All of them. Inside your systems, you handle errors, you transport data in and out of the boundaries, you archive some information, you do scheduled reporting maybe, and you do business logic. Yay! This doesn't even tell you what this thing is at all. This is what people normally call a logical view. It gives you those logical, conceptual, fluffy building blocks that we like to call architecture diagrams. Totally meaningless. Diagrams without technology choices. This diagram's kind of nice from one perspective, but I have no idea if this is Ruby or C# or .NET, C++, who knows. Homeless old C# objects. Big SQL Server database at the bottom, application thing at the top, lots of C# things. What are they? No idea. It's a really weird diagram, mixes different levels of detail, different levels of abstraction on the same picture. Crazy diagrams like this, representing event-driven, asynchronous style architectures, microservices, if you want to call it that. You start at the top, you go down through the picture. All paths lead to the trap over here. It's complex, it's all one color, it's cluttered, blah, blah, blah. This is why whiteboards are useful. We don't need this thing, we'll scribble it out. We don't need this line. Oh, yes, we'll put it back. And they say that naming is hard. So we're going to rename this thing up here. And if you take this to the logical conclusion, you get that. Yes. This was an entity relationship diagram that went wrong very quickly by scribbling out the important thing in the middle. So I have 15 gigabytes of photos like this that I could show you to fill up the remaining 50 minutes, but I think we'll stop there. I think you get the point here. Sometimes when I'm running this workshop, I actually hear people say this, right? They'll be drawing a box or a line or a shape, and they'll say, this doesn't make any sense whatsoever, but we'll present it later. We'll talk about this thing that doesn't make any sense on the diagram. I'm like, what? That makes no sense. Who says you're going to present your diagrams? Diagrams don't need to be presented. They are diagrams. It's a different medium. And of course, what's fun is if you break people up into groups and they have an hour and a half to do this exercise, they have an hour and a half of conversations and discussions and design to come up with some diagrams. And if you switch the context, either by switching the groups or switching the pictures, guess what happens? Nobody knows what's going on anymore. You get these diagrams that just make no sense to anybody. And that's basically where we are in the industry. And when you ask people to review these diagrams, they say stuff like, yeah, I'm not sure what these shapes mean. Why is this line pink? Well, somebody had a pink Sharpie and they used it. That's it. Why does this diagram show different levels of abstraction, different levels of detail? What do the funny symbols mean? There's a database-looking icon, but it's not a database. Now I'm confused. Yeah, this stuff's hard. I ask people, what did you find challenging about this exercise? And they say, pretty much everything, actually. Apart from doing the software design. The actual software design for this exercise is really simple. The drawing pictures part is super, super complex. And it's because people don't really know where to start. You know, if you have a solution in your mind, an architecture in your mind, a system that you want to build, how do you describe it? What type of diagrams should you be using to illustrate these things? What notation? Should we be using things like UML? No. Who said no? Some of the other speakers asked me last night, what are you speaking about? And I said, architecture diagrams. And they said, what, UML? I went, no way. So yeah, this is hard. I have no empirical evidence to back anything up. Right, this is all completely based on my experience anecdotally. However, I have run this workshop in 25 different countries for about 10,000 people around the world over the past few years. Software architects can't communicate software architecture. That is absolutely crazy given where we are today in our industry. And this, ladies and gentlemen, is exactly the problem I want to solve. So let's talk about UML. Who uses UML here? Oh, can we do one hand? 1, 2, I saw 5. Ah, you've gone to about 10 now, maybe. So what's that, 10 out of 500 people? That's not a very big percentage. Again, I've asked this question everywhere, and it's about 1 out of 10 people optimistically tend to use UML. So I'm not going to teach you UML. Hooray. I do use UML, but not for architecture. And the reason I don't use UML for architecture is that it doesn't really provide you a good set of abstractions to describe architecture. You can use UML, but you end up drawing silly diagrams like this, where you use a UML component to represent a software system, or a UML package to represent a software system. And you have to write software system in the box so that people know it's not a component or a package, it's a software system. And if you have to do this, you have to ask, why do I need these extra 2 little squiggles here? I'm just wasting ink when I print these things out. There's no point in using UML if you're going to abuse UML. So let's take a totally different tack here. Let's go and ask Google what it thinks an architecture diagram looks like. Has anybody done this? You should. It's hilarious. It basically just gives you page after page after page of very pretty, colorful Visio PowerPoint-style diagrams. And whenever I fly around the world and people let me see their documentation, which doesn't happen often, but when they let me see their documents and their diagrams, I see stuff like that. Does this look familiar? Do you have these sorts of diagrams on your wiki pages? It's okay to be honest. Excellent. I used to draw diagrams like this as well. I have also sinned, but I've seen the light. The light is currently shining right at me. So why is this important? It's about good communication. We've been banging on as an industry about Agile for the last 15 or 16 years and about moving fast, embracing change, and getting feedback. If we want to move fast as a team in the same general direction, we need good communication. That's essentially all this is about. It's that simple. So we have a couple of things to talk about. The notation you use is actually very, very easy to solve. So when I see people drawing diagrams, they make a lot of notational faux pas and errors, and they can be fixed very, very simply by just thinking about your notation. You know, having a title on your diagram really helps. This is such a stupid tip, but nobody ever does it. If you're going to have lines on your diagrams, make sure all of your lines are labeled as far as possible. Right? If you can use colors and shapes, make sure there's a key or a notation to describe the colors and shapes that you're using here. And we often joke that naming's hard. Do you think naming's hard in software? Yeah. So if naming is hard, it doesn't make any sense that most of our architecture diagrams are just named boxes, because there's such a degree of ambiguity that creeps in here. So my simple advice is just to add more text to your architecture diagrams. The text that describes something about responsibilities. And it gives you a really nice, quick, at-a-glance view of where your responsibilities lie across your architecture, for example. So this stuff's really easy to fix. You know, just be conscious of your notation. This is a really good example of that principle in action. This is what we see typically with diagrams. This is my approach. Lots more text, much, much richer pictures. Right, so content. Content's a much more interesting thing to discuss here. This is a quote from Philip Critchton's 4+1 model. He says, to describe a software architecture, we use a model composed of multiple views or perspectives. The 4+1 model looks like this. There's a logical view that describes your conceptual, fluffy building blocks. There's a development view that talks about the code elements. There's a process view that talks about concurrency and parallelism. And there's a physical view that talks about infrastructure and deployment. Do people use this? No. One. There are lots and lots of variations on this theme. So every architecture book has their own variation on this theme. Some of the names are the same. Sometimes the names are different. The thing you'll notice about all of these different ways to describe architecture is you get this funny separation between the logical view of your system and the development view. Fluffy building blocks, code. That's kind of odd. If you look back historically to some of the design approaches that we followed in the past, They have this logical or conceptual design phase and then a physical design phase. And I think that's led to this situation where we think of our systems as being different from a logical perspective versus a development perspective. Maybe this is also to do with we have architects produce the logical view of the system, and then they give that to coders who produce the development view of the system. So again, you get that gap between these two views of the world. And this is just weird. I don't like it. Because it raises this point that many people make. Yeah, we have architecture diagrams, and they show our logical, fluffy components, but they never quite match the code. Does anybody here see this a lot? Yeah. And if your architecture diagrams don't match your code, they're basically lying to you. They're useless. And again, that's a problem. A friend of mine, George Fairbanks, wrote this awesome book called Just Enough Software Architecture. And in this book, he talked about the model code gap. For anybody who came to my talk here last year, this is what I was speaking about. And it's how to join up the logical view of the system with the development view. And this is very simple to explain. So when we're having an architecture discussion, we use terms like module, component, service, and layer. But our languages, the languages we use to program, do not contain these concepts. So for those of you who are Java developers here, there is no component keyword in Java, is there? There is no layer keyword in C#. But when we create layers and components, we're assembling namespaces, packages, interfaces, and classes together to form these higher-level building blocks. So the two worlds don't quite match. The architecture view of the world and the code view of the world don't quite match. We use different terminology to describe the things in each. We need to step back slightly further to even attempt to solve this problem. Because even in 2016, we don't have a common vocabulary to describe software architecture. This is a pretty bold thing to say in 2016. But I can prove it to you with a quick quiz. Who likes a quiz? One person. Excellent. This is going to work really well. Right, so what is this? Come on, people. Otherwise, I'll get Edwards back on stage and he can rouse you up again. It's a map. What's it a map of? Riga, hooray! So what's this blue thing? A river. What is a river? Continuous flow of water. Yeah, body of water, perfect. So we know what this is. We know what a river is. We know how to walk outside and identify more rivers. What's this? So floor plan for a bathroom. Perfect. What's that thing there? It's a toilet. What is a toilet? Why are you laughing? Don't you know? This is going to be a smelly conference. It's another continuous flow of water. One way. Right, so we know what a toilet is. We know how to use our knowledge that we probably learned when we were about 2.5, or maybe later, to go and find more toilets in the building. This is a circuit diagram. What's this thing here, the squiggly thing? It's a resistor. What is a resistor? Resists something or other. Currents. If I had a box of electrical things at the front, like capacitors and switches and resistors, could you come to the front and rummage through the box and find me a resistor? Right, because you know how to identify a resistor. You know what it is, and if you knew the color coding, the stripes, you could tell me how powerful and how many currents it could resist. Right, so this is a really stupid, simple, easy quiz. Let's ramp up the complexity, because why not? What's that? Why are you laughing? This is your world. Right, let's go back to basics. What types of diagrams are these? This is UML. Specifically, what type of UML? And don't say old UML. So it's a collection of UML component diagrams. Right, so given these are component diagrams, what are each of the boxes? Components, thank you. What is a component? It depends. Who said it depends? That is like the perfect answer, though. It does. It depends. It depends on lots of things. I ran my workshop last week, and somebody said a component is an imaginary thing. Right. And here we have a diagram of imaginary things. So these are all components. We're not sure what a component is. This one here is stereotyped database, and it has a JDBC interface. So this looks like our database component, like something we deploy and run. The ones on this side are labeled application or UI. I don't know if these are mobile apps or web apps or desktop apps. The ones in the middle here are just bonkers. I have no idea what these are. I don't know if they are standalone deployable microservices or whether they are components that run inside these applications. It's the same with this diagram over here. Look, we've got a component representing a database, a component that represents business logic. Who drew this diagram? A component for a web server, a component for a firewall, and a component for ASP pages. Oh, blimey. And this is our problem. To boil this down to its absolute essence, imagine we are building a web application that talks to a database. Let's call that our software system. The word component means this, part of a larger whole. For some of us in this room, this web application is a component of the entire system, right? It's part of. For other people, that logging component is a component of the web application. So both of these uses of the word make sense given the dictionary definition. So we use the same words to mean different levels of abstraction, and that's just crazy. I thought we were supposed to be an engineering discipline. Nope, not yet. It's the irony of the ubiquitous language. Any DDD fans here? Yay! So DDD is about creating a ubiquitous language between us as techie people and the business people. We don't have a ubiquitous language for us in 2016. That's basically what I'm saying here. So how do we fix all of this? Well, UML tried to do the create a notation and create a set of abstractions that make sense, and it didn't really work. So I suggest we go back to basics, and we first agree upon a set of abstractions. And then we do the let's make the funny squiggles to create a common notation, like we have in electrical engineering, for example. If this sounds a bit foolish, given where we've been historically, let's go and get two maps of Riga and lay them out side by side. The two maps of Riga will show you the same things, the same abstractions, but they might use differing notations, color codings, symbols, line styles, and so on. Same things, same abstractions, differing notations. How do we decipher the two maps of Riga? There's a key in the corner. So the key or the legend in the corner helps us describe and understand the notations that we're using. And that's such a simple, powerful concept that we can take into the software world today, right now. So how do I do this? For me, a software system is made up of a number of containers. A container is simply an executable thing that runs your code or stores your data. In real terms, it's a client-side web app, like an Angular web app, a JavaScript, Java on the server side, Node.js or whatever, a database, a file system, a batch process, something like that. When I look inside my containers, they are made up of components. So I want to use the word component to mean something running inside an execution environment, a container in this case. It's a grouping of related functionality behind a nice, clean, simple interface. And because I mostly deal with Java and C#, my components are built from classes, and we're done. So this is a really, really simple model to describe the static structure of a software system. Software system is built from containers, containers contain components, components built from classes. If you're using JavaScript, that probably doesn't make much sense. So maybe it's modules and objects, or modules and functions. F#, Pascal, modules and functions. So you can take the same hierarchical approach and map it to the technologies that you're using. With this in mind, we can then draw some pictures. And this is what I call my C4 model in my book. There's a system context diagram at the top. You zoom in to show the containers. You zoom into each container to show components, and then optionally you can zoom in and see classes. If anyone's familiar with something called Schneiderman's mantra, Schneiderman's mantra is a way to deal with big data sets. Essentially, you get an overview first, then you zoom and filter on anything you're particularly interested in, and if you want the nitty-gritty detail, you can get that on demand. And as developers, we know where to get this stuff. It's in the code. It's in our IDEs. So that's why I advocate, don't draw this level of diagram, because we can get that very, very simply. Let's go one level up. Really quick example just to set the scene. When I moved back to Jersey in 2008, I built this thing here called techtribes.je. It's not working anymore, but it's just a content aggregator for the local tech industry. This is a context diagram. So that's the system I built. There are different types of users and different systems that we depend on. If this was interactive, we select it, we pinch to zoom in. We see the containers inside it. So inside the TechTribes system is a web application, a console application, and some data stores. We select that particular process there. We pinch to zoom in. We see the components inside it. Same sort of deal. All of these are components running inside that console application. We pinch to zoom in on this component. We see the code. So for those who came to my talk last year, it's these final two diagrams that often don't make much sense. The mapping between a component on a diagram and a component in the code. So that's what that was all about last year. It was about good design and modularity. This talks more about diagramming. So these diagrams are essentially like maps. That's the whole point of this thing. So if you go and do a search for Jersey on a smartphone with Google Maps, you'll get that picture. Zoom straight in. Sometimes this is really useful. If you don't know where Jersey is, it's totally useless, so you have to zoom out a couple of notches. The software diagrams are the same. Sometimes, as a developer, I want the zoomed-in view of the world, components, maybe code. And at other times, depending on who I'm speaking to, you need to zoom out. So different diagrams for different stories, and for different audiences. What I'm really trying to do here is create a static model of my software system. Right, this is very much a static model first approach. And once you understand the static model from the level of your system down to the code with a couple of levels between, you can weave other views in around really simply. So if you want to show how a use case or a feature works at runtime, you can show a UML collaboration or sequence diagram that shows how elements in your static model interact at runtime, for example. So this is good. I've now taught you how to draw diagrams. I may have skipped over a little bit of information here and there. Come to my workshop tomorrow. It's at this point people say, well, what tooling do you recommend? And it's normally now someone says, whiteboards, paper. It depends, yeah. What I see a lot of teams doing is they use whiteboards, they use pieces of paper, and if they need to document systems in a formal manner, they take those diagrams and they throw them into some tooling like Microsoft Visio, OmniGraffle, Lucidchart, Glyphy, Draw.io, etc., etc., etc. Because these diagrams I've shown you are just boxes and lines, they can be drawn with any general purpose diagramming tool. You create some boxes, you create some lines, you wire them all together, it takes you forever, but you get there in the end. It's 2016, people. No. This is very bad. Please do not do this. Our friends in the building world do not do this. Right, imagine they were creating this grand library. Do you think they got Visio out? They might have done, but I don't think they did. I think they've probably got a modeling tool out, like AutoCAD, and they started creating a nice three-dimensional model of what this library was going to look like. And then they can surface and draw different views based upon that data. Do you know the irony of this, by the way? Hands up, who's a software engineer here or software developer? Who builds software? That's all of us. We build these tools. We cannot do this for our stuff. This is crazy in 2016. Now, the one thing we do have to our advantage is that we have code, and we can reverse engineer code into diagrams. Who has tried this? What happens? Bad things. Do you normally get messy diagrams? Is this because your code is a mess? No. No, 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 no. You get messy diagrams because the diagramming tools are showing you everything. They're showing you code. They're just reflecting all of the code straight back at you in a really horrible format. Really simple example. So in the Java world, there is a framework called Spring. Spring does everything. That's all you need to know. And as part of Spring, there's a part of it called Spring MVC. It's a web MVC controller framework. And there's a sample application called the Spring Pet Clinic. And it's a really simple toy application that showcases and illustrates how to build web MVC-style applications. This is the diagram that the Spring team uses to summarize the architecture. There's a bunch of view stuff, HTML, CSS, whatever. There's a controller layer, a service layer with business logic, and a repository layer. It's just a boring three-layer architecture. And if you came to my talk last year, you'll know why I said boring. And this is what the code looks like. So there are a bunch of entity, domain, value object type classes. There's a bunch of repository classes, which is that stuff. There's a service package, which is that stuff. There's a util package, because why not? And you have util code, right? I do. And there's a web package, which is this stuff here. So given this is my code base, my project I'm working on, if I use my tooling to reverse engineer a diagram of this code base automatically, I get that. I did try. It's really hard to get the lines to not overlap. I gave up after 33 seconds, to be fair. It's just really hard because it's showing you everything. It's showing you all of the interfaces and classes in this code base and all of the dependencies and relationships between them. And this is a toy application. This is not your code base with a million lines of code. So as a strategy, this is just not going to work. We can get something a bit better by removing some of the less important code types. So in this case, I've removed the entity classes, the domain objects, and the util classes, and I've shuffled around the boxes to almost recreate that layered architecture. So we have the controllers at the top, that's the service thing there, and these are the repository classes. So this is a bit better. However, this is still a toy application. Let's go back to maps. If this was a Google map, this might be like Street View. So imagine I come to Riga for the first time, I get outside the airport, and I'm totally lost. And I open up my smartphone, and I switch to Street View. Is that a really dumb way to navigate an environment? Yes, because I have my phone here with Street View, and the Street View here. And this is essentially what this diagram is showing you. It's like, here's the code, and I can see the code, I still don't understand what is what. You know, I can't understand the layering here, for example. So let's zoom out to get back to that overhead view. If we zoom out, I think the diagram we really want to draw is something more like this, where each of these blue blobs, that is a technical term, each of these blue blobs represents a component. And what I'm doing here is I'm identifying what I think are the individual components in this code base. Each of the controllers, I think, is a separate component, and I'm bundling up the interface and implementation class for everything else. This answers a bunch of questions, but there are still some funny helper classes kicking around on the edges, but we'll sort those out later. So the problem with these tools that reverse engineer diagrams from code is that they see code. I know that's how they work, but that's the problem as well. And they don't understand what a component is. So if I'm reverse engineering a diagram from a code base, I don't want to see code, I want to see components. I want to see that one level up. This is not a new problem. There's a paper from the 1990s, and it basically says if you ask anybody working on a project to draw you a diagram of that system, you get a very high-level picture. And that high-level picture represents the high-level mental model that that developer has of the system. If you reverse engineer a diagram from the code, you get a very low-level, very accurate, very precise picture. But it doesn't match the way that the developer necessarily thinks about the code base. It's that model code gap thing again. That's essentially all this is about. The big problem with code bases is that the architectural information typically does not exist in a code base given the languages that we're using today. So because we're not programming in terms of components in our languages, it's really hard to find that information just by scraping the code base. And that's why most reverse engineering tools do a really, really poor job at this. So we can fix this. So I've created some tooling called Structurizer. Structurizer is a tool of many halves. There's a web software as a service thing. There are some commercial plans on this as well, but everything I'm about to show you is totally available for free. So I'm not trying to sell you anything. If you go to Structurizer right now, there's an express link on the top, and without signing up, you can draw some architecture pictures. So if you are familiar with plant UML or web sequence diagrams, where you write some text and you get some pictures, you can do the same thing. So if you want to stop using Visio to draw some simple architecture diagrams, this is a really good approach. However, this is not where we want to go with any of this, because this is still creating diagrams manually. George Fairbanks to the rescue. In George Fairbanks' book, he says we should minimize and reduce the model code gap by adopting an architecturally evident coding style. An architecturally evident coding style is basically dropping hints and metadata into your code so that your code reflects your architectural ideas and intent. This sounds very grand, but it's really very simple. Stuff like this. So if you have a box on an architecture diagram labeled logging component, make sure there's something in your code called logging component, right? Make sure the names match. Maybe have a namespace or packaging policy where every box on a diagram represents a package or a namespace or a folder in your code base. Maybe add machine-readable metadata to your code so that your code reflects your architectural ideas. This is a component. This is a module or something like that. There's something called an architecture description language, which not many people have heard of. And an architecture description language is a textual way to describe software architecture. There are a bunch of them out there, Koala, Darwin. They're mostly used in the Netherlands and Germany for reasons I don't quite understand yet, but I'm getting there. And although these architecture description languages have never really made it into mainstream development, they are text, right? They're textual descriptions of architecture. And as developers, we like text. We have tooling to support text. We can diff text. We can version control text. We can do a lot of stuff with text very simply. So this is a great concept, but again, I don't want to teach you something that you're never going to use. So what I've done instead is I've created something else, which I call an executable architecture description language. And this is basically describing your architecture using code. And there are two open source libraries, both on GitHub, one for Java, one for .NET. And basically, they allow you to write code to describe architecture. In the simplest concept, they are implementations of my C4 model in code. If we go back to my Spring Pet Clinic application, let's figure out how we define the architecture for that system using my Structurizer stuff. So the Spring Pet Clinic system is nothing more than an employee of the pet clinic using the system. So we can model that with code. This is just a little Java program. We create a software system object to represent the Spring Pet Clinic system, a person object to represent the employee, and we say that the employee uses the system. Done. From a container perspective, this is nothing more than a web app talking to a database. So again, we can describe that with code. We can create a container object for the web app, container object for the database. We can say that the employee uses the web app, and the web app uses the database. Cool. I don't want to have to do this when I get down to the level of components, because there are lots of components in most systems, and they change a lot. So built into both libraries is something called a component finder. The component finder finds components. See, naming's not hard. Just think about it. And what this does is it allows you to plug in different strategies to find components. Of course, every code base is different, and every code base is unique. So how do I know how you've built components? And the answer is I don't. So that's why there are pluggable strategies here. And one of the strategies you can plug in is this pre-built Spring Component Finder strategy. And what it does is it goes and finds the Spring annotated classes. So if you're building a Spring MVC application, you annotate the special classes at controller, at service, at repository. So what this does is it goes and finds those things. It understands the Spring naming conventions. It bundles together the interface and the implementation class. It calls that block a component. And it also goes and finds the dependencies between the components using static analysis and reflection techniques. So you basically run this on the compiled bytecode of your application. So you go find components. You can write some more code, because basically what you have now is a little object graph in memory of components and their dependencies. And you can say things like, go and find me all of these Spring repositories you just found and make them use the database. So you can start to wire up other parts of the model very, very simply. That creates your model. We can then create some views, some diagrams. So there's a system context view, a container view, and a component view. And these views map onto the C4 diagrams I showed you before. And we can add and remove various elements from those views to customize what the diagrams show. We export it as a big JSON document, because why not? And we upload it to Structurizer's web API. And you get some pictures. So this is the context diagram for the Spring Pet Clinic system. It's the employee using the system. This came from the code I showed you. This is the container diagram. It's the employee using the web app using the database. Again, all this came from the code you saw. And that is the component diagram generated automatically from the code. I have to caveat this. Structurizer does not give you automatic layout. Oh. So all of these green blobs are the components from the Spring Pet Clinic web application. Some of the names should look familiar from the class diagrams I showed you before. The dependencies have been discovered automatically. This text here actually comes from the source code. So this is the top-level Java.doc comment on the type associated with this component. So again, I'm trying to pull together multiple sources here to create a decent set of architecture diagrams that stay up to date when the code changes. See, what I've tricked you into doing now is I've tricked you into creating a model of your application. Modeling is something we used to do like 10 or 20 years ago around software design and architecture. But modeling went way out of fashion. And I want to reintroduce modeling as a thing we do. Because once you have a model, you can do stupid things like generate diagram keys automatically. Yay. So as long as you're not fixed on the notation you want to use, a lot of the really boring, trivial stuff goes away. We have a set of maps. That's essentially what this is all about. We have a set of maps that represent the software system at different levels of abstraction. And actually what you can do is if you go to the live version of these diagrams on structurizer.com, you can double-click that system box to get to the containers. You can double-click that container box to get to the components. And you can double-click a component to get to the source code on GitHub. So we've got a set of maps continuously opening up and zooming in and zooming in and zooming in until we get to the code. And that's a really simple, powerful feature, because now it gives you a set of maps to give to a new joiner so they can start exploring your code base. Right? They get that top-down overview, and then they can dive into detail. So the open source libraries are open source. The structurizer.com thing has a free plan and some commercial plans. You can use the open source libraries and do whatever you want with the output. Because you have a model there, you can visualize the model in a number of different ways. And here are some examples. So built into the Java version is a GraphViz exporter. Any GraphViz fans here? There's usually a few, yeah. So with Graphiz does automatic layout for you. So you can create your model and your views with Structurizer, the open source library, output it to a dot file, loads the dot file into Graphiz, and gets some really ugly diagrams. However, they are laid out for you. I am told you can make this look pretty, but that's too hard. And for those of you who like plant UML, there's a plant UML exporter. So again, you can create the model and the diagrams in Structurizer, and you can export the plant UML definitions to load into plant UML. The benefits of using Structurizer alongside plant UML is that you have a model. So if I change the name of this person, this user type, it changes in all of the other diagrams. So the model gives you consistency. If you hook all of this up with your build process, guess what happens? You get continuously up-to-date diagrams, real models of your code base, and that's exactly what this is all about. You can also do some more cool stuff. So once you have that model, you can explore your model, and you can start asking the model questions. So since it's a tree structure, we can draw the tree structure. So this is the tree structure for the Spring Pet Clinic system. There's the system, there are the containers, the components, and these are all of the code level elements that were found in the code automatically. If we zoom in, we can start applying different highlighting and color coding. So that's the component type, and these gray faded types here are shared code. So these types are shared between this and other components. And again, that gives you some information that you might not have spotted about your code base. If you have a map of your components, you can draw a dependency map. So these are all of the components in the Spring Pet Clinic web application. I've highlighted this thing here, the clinic service, and this is now showing me all of the inbound and outbound dependencies. Again, if you had cyclic dependencies, you could start to highlight those things on these maps too. If you have access to the source code, you can start ranking and rating these things based on size and complexity. So here is a diagram showing the components in the Spring Pet Clinic web app ranked based upon size, in other words, numbers of lines of code. So you can see which components here are the largest. If you were to double-click on one of these, you get down to the code level. If you like this type of thing, I definitely recommend you go look at Adam Thornhill's code scene tooling by Empire, because they've got a lot of this stuff, plus a lot more, especially around the kind of social factors, human factors. So, summary. Please stop using Visio. No, that's not my summary. No, it is my summary. The 1990s are calling. Please stop using Visio for doing this. Right? This is not state of the art. Visio is not state of the art. Nor is Glyphy or Lucidchart or Door.io. Let's start treating software development as an engineering discipline, and let's start creating these artifacts properly. Right, so let's stop using boxes and line sorts. Tooling to one side. Right, if you're still going to use Visio, think about your abstractions first and let the notation evolve. So my biggest tip for you this morning is whenever you're having an architecture discussion with a view to describing it, communicating it, or visualizing it, make sure you understand the abstractions that you're using to describe your system. That's the biggest thing here. With that in mind, I hope you've enjoyed that. Thank you very much, and enjoy the rest of DevTernity.